Roger Steger. Whoops. And I wanted to say just a couple words kind of before we got started to set somewhat the tone and format. When Ted first was looking for volunteers and asked me to present, he kind of defined, and I think he went over in the outline in the first week, the format that Ted envisioned, which is one, we expect the majority of the participants to have read the section ahead of time, so kind of be prepared for that. And then two was that each week he was looking for somebody to volunteer to present a chapter or a section out of the book. And with that, he gave me the caveat that that you don't have to be an expert to lead a section. I think that having that style of having individuals lead the sections lends to a much more interactive meetup. A lot more people. You're more invested if you presented a section. You're more invested in the whole thing, and you're also more comfortable speaking up and asking questions, or speaking up and answering questions. So I like that style, and I'm looking forward to that. It might be a little bit hard because I don't know how many participants we have this week. 20. That's down a little from last week, so that makes it a little easier. I think it's easier with smaller groups. But anyhow, we'll see how that goes. So the other part is the discussion leader doesn't need to be an expert. That's important. We saw Neil did an awesome job last week on that section. We're going to do the other end of the spectrum this week with me. I am not an expert. I'm a beginner in this space. I'm a software guy. I'm not a data scientist. I have not had any formal training in probability. I've bumped into it a lot in my machine learning journey, but I really haven't had anything structured. So as I'm going through this book, I'm not even the basics. I'm not reviewing it. I'm really learning it as I go, or not learning it. And I know that there are, at least in the breakout that I ended up with, there was several data scientists in that group, and I'm expecting that to be a reasonable sampling of our group. So I know there's other people with more expertise that hopefully will be able to answer questions. And you're going to learn a lot more from them than you are me. But I think it's going to be fun. So again, I'd like to think of this as a study session, interactive. It's not a lecture. If you have a question, if I say something wrong, which is likely to happen, please feel free to interrupt and correct me, and take the mic for as long as you want, type of thing. And I think we'll have more fun doing it in that style. So Ted, is that anything you want to add or subtract to that?
No, that's awesome. I appreciate it takes a certain bravery to volunteer, especially early on. So thanks for doing that. And yeah, so if you can lead the outline, and if there's things that you have questions, I definitely have questions about stuff, then I think, like you said, as a study session, we can see, and maybe somebody will be able to answer questions, or maybe some of them, none of us will. But yeah, I like to use the word crowdsourcing. Like for me, it's definitely a lot of value compared to just trying to read it on my own.
Great. And I'll, Ted, if you can keep an eye on the chat session or any hand raising or anything like that, and just make sure you interrupt me.
Yep,
if we do.
Happy to do that.
Okay. And so I thought what I'd do is I'm not sure exactly what the right flow is, but I thought I'd just kind of go through. I'll actually read from the book some of the sections that I've highlighted, kind of track what was my learning process, what was my observations as I went through, and my questions. I'm going to have questions I'm going to ask, because there's certainly parts that I didn't understand, and I'd spent quite a bit of time trying to get at it, but there's still areas that, yeah, I really didn't get. In terms of, let's see, this is the outline. You guys can all see that screen, can you? The probability book notes. Okay, so this was the outline for the first section, chapter 3. And I think we looked last week and said, gosh, that's a long chapter. We're not going to make it through it. So I've kind of set, I'm hoping we get down to like 3.6, maybe 3.7, something like that. And then I don't know, Ted, you were looking for maybe another volunteer for next week. Well, I don't know how that's going, but we'll see.
Yeah, I don't know. Actually, maybe I should ask early in case some people have to leave early. But just, by page count, actually, if you just get us through section 3-4, that's actually half the pages because some of the
Okay.
later sections are shorter.
Okay.
So that would be nice if we can do this in 2 weeks,
Right.
But yeah, so is there anybody here who could raise their hands to just lead the discussion again? Doesn't say anything about being an expert, but just to kind of, be that person to walk us through the outline next week.
Okay. Well, people are contemplating that, then let's go ahead and get started. So, all right. So this is where it starts. So again, I hope you don't mind the format, but the words are probably easier read. I'll paraphrase when possible, but sometimes just read directly. So the introduction, probability theory is concerned with modeling the distribution over observed data outcomes, D, given known parameters, data by computing. What's the proper way to say that? Just P of D given theta? Okay, by contrast, statistic is concerned with the inverse problem, in which we want to infer unknown parameters theta given the observations, actually, i.e. we want to compute P of theta given D. In fact, it was originally called inverse probability theory. And nowadays, there's 2 ways to do that. Frequentist statistics and Bayesian statistics. And Bayesian is what we're going to be studying mostly here. I had an interesting little thing in one of the videos that I watched, just as a little trivia. It turns out that Bayes originally came up with the Bayes rule somewhere during 1740s. His paper wasn't published until his death. And it was actually Laplace that kind of reinvented it and started applying it to scientific applications and kind of came up with the idea of conditional probability and prior probability, et cetera. And he popularized it, but it retained the name of Bayes. So, and he discovered, I guess Laplace also discovered the Bayes paper after it was published. So he gave credit to it. So it's interesting. Another one of those, where does the credit go in history? It's not always to the originator. Okay. So in Bayesian approaches statistics, we treat parameters theta as the unknown and D as the fixed and known. We'll see the opposite of that when we dive into the frequentist approach. We represent our uncertainty about parameters posterior to seeing the data by computing the posterior distribution using Bayes' rule. So now this was something that we saw back in, let's see, chapter page 40 in 216 when it was originally presented to us, and it was presented as events. So the likelihood or the probability of event 1 given event 2 is the probability of event 2 given event 1 times the probability of event 1 divided by probability of event 2. So that's what we've seen. And now what we're going to do is look at it from the perspective of these unknown parameters. So P of...
Roger, one difference there is that the previous one that you showed is a probability. And what we are seeing here now is a probability distribution function. And so there's a little bit of a difference there.
Okay. So I don't know, did Bayes pose it as a probability or a distribution? I'm not.
Probably Bayes did it as probability, but the integral there suggests that it's a probability distribution function.
Yeah,
and just historical note, Bayes himself wrote shockingly little on this because he was a reverend in the Anglican Church. So like you want to go back to like Laplace and Gauss if you want to see like the actual mathematical development instead of like first guy that had the thing in print.
Okay. Yeah, I actually read where Bayes used a lot of frequentists. That there's a link in here which I can transfer over that goes through, and actually even the Wikipedia covers kind of the history of a Bayes approach, a Bayesian approach, and then frequentist approach, and back and forth.
What are you, a little bitch? You're my Andrew motherfucking Tate. You ain't got button up shit. I'll walk into the fucking most.
Okay.
Sorry, guys. Thanks,
So,
Ryan.
And Janeth, when we talk about maybe, you know, when I say P of theta given D, the parameters given the data, what's the correct term? Do I call that? I look at it and think of it as probability of theta given D, but I know it's not a probability. I know that's a probability of density.
Yeah, it's exactly what it says. It's a density function. So
Okay.
you can think of it as a function of theta.
Yeah.
So, you know, it's no different than any other function that you know of, except that it has a little bit of special properties. That if you integrate it from minus infinity to infinity, you get 1.
Okay.
But,
So
and then the probability of that value theta, you know, here theta is a vector. I think that's why it's in bold. But if you imagine that it's a scalar, and forget about the conditioning on D. If you just think of it as P of X, let's say, and you know they denote the random variable as capital X. So if you want to figure out what is the probability that the random variable capital X is between two values A and B, you integrate between those two limits. So that gives you the probability of X between A and B.
Between those two limits, yeah. Okay, so I got that. So what I'm hearing now is
what it is, yeah.
So I should just, shouldn't call this probability of theta given D. I should call it just P of theta given D. Is that right?
Yeah, that's what I would do. Yeah.
Okay. 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 So going through this, so P of theta is called the prior, so represent the beliefs about the parameters before seeing the data. P of D given theta is called the likelihood, represent our beliefs about what the data expects, about what data we expect to see for each setting of the parameters theta. And then P theta of D, or given D, is called the posterior and represents beliefs of the parameters after seeing the data. And then lastly, P of D is called the marginal likelihood or evidence. So there's a few things, and I don't, one of the questions is, I didn't understand this term here, this integral. What is the theta prime?
So the theta prime is just a variable of integration. You could have used anything, X, D, Y, whatever you wanted to call it, because when you integrate it, it goes away. So you're integrating from minus infinity to infinity, right? They don't show the limits.
Okay.
But you can use any variable. And when you integrate over a variable, that variable will go away once you finish the integration.
So this would be for all possible thetas then?
Correct.
Okay.
All possible thetas. And they don't want to use the same variable theta to avoid confusion, so they use some other variable, and here they've used theta prime.
Okay. And if this is a vector, then it's over the entire vector space of theta.
Correct. So it'll be like a multiple integral over each. So theta 1, theta 2. So theta 1 over minus infinity to infinity. Or whatever its range is. So if it's 0 to 2 pi or whatever its range is, you just integrate it over the whole range.
Okay. So then my other question I had then is, so I always thought P of D was kind of the related to the distribution of D, like all D that could exist.
It is.
Okay.
And so what this is saying is that you can't get P of D directly. But what you can get is P of D given theta for different values of theta. And so therefore you can calculate P of D by getting all these different P of D given theta and integrate over it.
Okay. So should I think of this then as if this D represents my data that I'm trying to fit, right? It's fixed and known. So if I've got heads, right?
Yes.
P of D then represents what, the probability of that over heads, tails.
Correct. And so a couple of things, the heads tails is like a discrete random variable.
Right.
Imagine, wave your hand and say that it is continuous.
Mhm.
And if you have, let's say, if you have a biased coin and you want to figure out what the bias is, you don't know what the bias is, right? All you can observe is the heads or tails given the bias. So you can observe P of D given theta. And so, but you
Okay.
want to figure out what P of theta is given D. With the observation that you have, you
Right.
want to find out what the bias is. And so this equation here helps you go the reverse way.
Okay. And so maybe that makes me helps me to understand, because I've heard that denominator is hard to realize, hard to compute.
Correct. Because you want to do it over all theta. And so you can only do so many observations. And so you can observe it for certain values of theta. And so therefore that denominator is hard. But the key thing here, and I think later on maybe we will come across it, is that P of D is a constant with respect to theta. And so when you're differentiating it in order to find the minima and maxima, you can just ignore the denominator because only the numerator comes into play. So that's why it's while it is hard to compute, it is also inconsequential in certain cases.
Okay. Yeah, I saw that where a lot of times they were just dropping things all together and just using proportional rather than the absolute value. Okay.
And another thing is that suppose you for a moment ignore P of D and you're able to calculate some function, you can always integrate it and divide by that value to make it a distribution so that it integrates to 1. Does that make sense?
I think so, yeah.
And so from that perspective as well, people ignore P of D.
Okay. Okay. So the other one that I hate to struggle so much with the very first equation, 3.1, but the other one that I had an issue with here is P of D given theta. They call it a likelihood here. I saw a number of places where it was referred to as a likelihood function is not a PDF, is not a probability density function. And
so
I
if you're a
been able to
frequentist, the difference between a probability and a likelihood is what is the variable in it. So if it's the theta, then it's a likelihood. And if it's a probability, then it's the D in this notation. So with respect to D, it all adds up to 1, but not with respect to theta.
Okay. Okay, then that, yeah, because the likelihood I've seen expressed as L of theta given D. And so, yeah, that would make sense. Then it's in one direction, it is a probability, in the other, it's not. Okay, did anybody else have any questions on the first equation of the chapter?
I just want to mention where the integral comes. Do you remember the original bias formula when we have a ratio and then this one probability in the ratio, we can write it as a sum. If this event D, we can split in several events. And then we have probabilities of these small events multiplied by their likelihood. Do you remember this formula?
Yeah, let me see if I can find this.
Is
this one you're talking about? Yeah.
2.16 second part. Yes.
Yeah. Or
yeah.
continuous 2.17.
No, I mean actually, I meant probabilities.
Okay. Okay.
So when you take these events very, very little, and then your summation turns into limit of summation, and limit of summations is an integral. So this is how the integral comes.
Okay.
And then we consider this then we consider the density at each point. So we divide pretty much by the size of interval, very, very small interval. And since we divide it everywhere, we get density and not probabilities themselves. I'm sorry, is it clear or not?
I think so. I think so. There was an argument similar to that here in the Wikipedia.
Good.
Yeah, where they talk about, if you're trying to find the argmax of L is the likelihood function of theta given the data X, that they go through the algorithm of exactly what you talk about. They're smaller and smaller. It's a probability,
Yes.
but then you take smaller and smaller slices, and eventually that argmax is equal to the argmax of the density, the PDF X given theta.
Yeah, I think
Yeah,
how
good.
I would say what Maya was saying is that equation 2.16 is the discrete case. And if that seems reasonably intuitive, because you're like, oh, for flipping coins, it would be a countable number of cases, like 32 cases. And so I could just do all the different cases. Well, then 2.17 is really the same thing. It's just an integral instead of a summation for the continuous case instead of the discrete case. So if the discrete one just makes your brain happier, then lean on that for the intuition.
Yeah. Yeah, you can get to probability more quickly in the discrete case, right? It's when you're dealing with PDF, you have to stay away from that. Okay. Any other questions or comments, contributions?
Yes, kind of quick question for on the 3.1. Which of part is usually assumed and which is usually I don't know the right term for question to this, but I noticed that many part of this is assumed to have some form of distribution, and some part they just calculated from data. So can every part of this be assumed to have some form of function? Let's say follow normal distribution and just take it as is or something like that.
So I think I can answer that one. I think that this P of theta that's the prior, that's the one that you have to make a guess at least the first time before you have any data at all. You make a guess at P of theta. When you observe data, you look at the likelihood of the data given that assumption, and using Bayes' rule, from that, you're able to compute the posterior, which is your updated perspective or updated belief on what the theta is, the parameters are, having seen now that data. Did I do okay on that?
But the specific likelihood you're using is also you're making a strong assumption there about different distributions. Like if I just told you my observation is 7, like you can rule out a couple distributions, but there's a lot of other ones that you have to pick from.
Okay.
So assume that the upper
So you
part
make-
is a form of function, and people impose a strong assumptions on the density of it, right?
Right, Favis, and I kind of jumped ahead in my comment there. So in section 3.2.5, they formally talk about the prior, where they say that the prior is, as Roger was saying, is related to our beliefs about the observable outcomes. So some prior beliefs, basically. So it is some abstract quantity is what they are saying, not, I mean, they say not directly observable, but basically our belief based on the observable outcomes is what the prior is, like before we started our experiments.
Got it.
And
Thank you.
I didn't catch who made the comment, but I guess you're also right that there's the assumption about the model that you're using for the various distributions, for both the model distributions and the observation distributions.
Got it.
Yeah,
Thank
and
you.
I think in this chapter he does talk about what models are, and I always think of them as like two parts. There's distributional assumptions, and then there's like a functional form if you're trying to, like, I do a lot of GLM, so you're interested in like the functional form of variables related to the conditional expectation or the mean or whatever. So like model encompasses all of that.
Right.
See.
Okay.
Yeah, sorry
Yeah,
for the big
and maybe,
pushback.
no, this is good discussion. I think maybe when we get into the next subsection with the actual coin tossing, then hopefully that'll be a little bit more concrete.
Got it. Yeah.
Right. And
Yeah.
yeah,
Quick remark, and yeah, I usually notice that people would say that these upper part are adjustable, but I usually see that people assume some specific function for the things as some kind of imposing constraint to the model. So there's just a quick question to get out there.
Yeah, and
Right,
one reason they do that is, you boil down your problem from figuring out a distribution that you had no idea of to just determining the parameters of the model that you have assumed. Of course, there's a question of did you assume the right model, but the problem, you've made the problem simpler for yourself.
right.
Okay.
Just one comment, Roger. You asked any more comments on this
Yeah,
one? So,
absolutely.
So p theta on the right hand side, there the theta is the distribution of the prior. So that's, even though they're using the term theta left and right on the left side of the equation and right side of the equation, on the left side is the prior distribution. Oh, sorry, right hand side. And the likelihood that PD given the theta is based on that prior theta. But on the left-hand side is the distribution of the theta variable, which will be a different function after the data is observed. So, I mean, it probably will become more clear when we go to figure 3.1, when they will talk about different functions for, which may be next page, I don't know, but yeah, or it's section 3.2, yeah. Okay. So maybe I'm just jumping a little ahead and okay, maybe after tossing coins, as Ted was saying. So let's go through that and it will be more clear.
Okay, one last shot. I think this is it. There's been a lot of time on it, but I think it is kind of a big part of this chapter. So if anybody else has any other questions or comments, clarification. Okay. I'll go ahead then and move on. So what he does, the author does here is uses as a way to kind of dive in this tossing coins example. We're trying to figure out this coin, is it a fair coin? And I'll go through this. We'll go through on this first section as he does, dive through the math a little bit, follow along on that. Later on, I'm going to have to speed up because I didn't get into the math later on near as deep. So, but anyhow, so we're going to do tossing of coins. Theta is a parameter. It's somewhere in the, I think that's a closed interval from 0 to 1. That's the chance that it comes up heads, which we'll denote by y equals 1. So y equals 1 is a heads. We toss it n times and we record the outcomes as the data is equal to the output is a 0 or 1. So yn is a member of the set 0 to 1 for n of those. And we're going to try to compute our belief posterior of theta given this data set. Okay, so first of all, we assume IID, this is independent and identically distributed. I added this term, I'm not sure that that's correct, but it's basically the distribution of D. And so what we're saying is what's the joint probability of all of the yn in D given a theta, where theta again is the probability that when you flip the coin, it's going to come up heads. And this is a little kind of switching mechanism. Since y is 0 or 1, if it's a 1, this term will be theta, and this term will be to the 0, so this will just be 1. And if conversely yn is tails, then this will be 0, so that term will be 1, and this term will be 1 minus theta. So the assumption is that if it's 0.6 probability of coming up heads, then it's 0.4 probability of coming up tails. So it's assigning the probability to all of these. If you factor those all out, you get theta to n1 and 1 minus theta to n0, where n1 is the number of heads, and N0 is the number of zeros. So what does that mean? Why theta? Theta is probability of coming up heads, isn't it?
Yeah, theta is the probability of coming up
Yeah.
heads. We're going to have N1 of the heads and N0 of the tails.
Oh, yeah, yeah, okay. Yep.
And
Okay.
another thing to point out,
That's-
you know, the IID here is that the YIs are IID, right? And so your second toss doesn't depend on the first toss. They're all independent. And all
Right.
your tosses come from the same distribution. It's not like there was wind blowing on the third toss and it came from a different distribution.
And this distribution here is going to be determined just by theta, right?
Right. So
Okay.
you just need the probability of heads because you can get the probability of tails as 1 minus that. And so
Right.
the probability mass function will have, you know, two values, one at 0 and one at 1.
Okay.
Yeah. So just a quick note, Roger.
Yep.
So I think you might have slipped. You said the joint probability, but this is the conditional probability, the probability of D given theta. Okay. And if you look
I'm
at,
sorry, when I said joint probability, I meant the joint probability of all the heads and tails.
oh, okay. All right.
Yeah.
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 So that
that's
expression
why
on the
it's
right,
Go ahead.
that expression on the right, is a function of theta. And you will get a specific value for any given theta. In this case, theta is a scalar. You will get a specific value for any value of theta that you pick between 0 and 1. Right. So this is a function defined on the range 0 to 1.
For theta.
Right.
Yeah.
So
And
P
then
of
the
D given
D,
theta on the left is a function. And is a function defined on the range 0 to 1.
okay, maybe I misunderstand then, because there's the data. So there's a theta that determines this, but there's also the data that determines the YNs, right?
Yes.
So if you look at P of D given theta, it's a continuous function of
Right.
theta. I think that's what you're saying, right, Ted?
Yeah. I'm just trying to clarify that that's a function. That's not an expression. It doesn't have a single value. It's only if you plug in a value of theta, right? So yes, you're right, Roger. The D is what tells you how many heads that we're looking at. So if you did 10 tosses and you got 7 heads, then you got 7 in the first expression and 3 in the other one, or whatever in the exponents.
Mhm.
Does that make sense?
I think so, yeah.
Yeah. Okay.
Sorry. I get a little, it's a little confusing for me in that this function P requires both the data set and the parameter theta, right? So in a way, it's a function of two variables, but we're saying theta is fixed,
So
right?
No, it's not fixed. It's not fixed.
theta is
That's
not
what I'm saying. Just think of it as a function. So if I said f of u comma v equals u squared times v cubed, it's just a function in 2 variables.
Mm-hmm.
So this function on the left, p of d comma theta, is just a function in 2 variables. How many heads and what's the coin thing? And you could graph it as like this 2-dimensional surface where theta is between 0, 1, and heads is whatever, it's discrete, I guess, but it's between 1 and 0 and n.
Like if you look at the rightmost expression, n1 is a constant, n0 is a constant. The only thing that's variable is theta. And so
Right, for a given data set, it is.
For given data, right? But
Given
P
data.
of D generically would be valid for any data, for any
Right.
n1 and n0.
correct. So P of D,
Yeah.
where you know already what D is, n1 and n0 are fixed. Yeah.
So sorry,
Yeah,
Roger. I thought I was helping, but I don't know if I'm actually
No,
helping.
well, no, actually, if it's off topic, I'll move on, but I think it is, I'm not sure the difference between when I say P D pipe theta, the vertical line theta, versus P D comma theta. I thought it meant that the joint probability of D comma theta would be the two-dimensional space. And this would be a one-dimensional space where you've conditionalized it on theta, A theta.
Right. So that's where I was trying to clarify that it's not true. It's still a function of two variables. Okay. So if in my old example, f of u comma v is u squared times v cubed. If I want, I can give you a specific value of u, and then it's just a function of one variable, v cubed. Right. So I can give you a particular data, and then it's just a function of one variable, theta. But originally, it's a function of two variables.
Okay.
All right. And so
Roger.
this is the f of something comma something, that's the joint probability, but this is the conditional probability. And you could, if you wanted to graph, it's discrete, so it's, but you could graph for a given theta what the different d's look like.
Yeah.
So,
Yeah,
and then if you plug in both values, then you just get a single point.
I look at this as a single, function of theta alone. Like you toss n times, and you observe n1 heads and n0 tails, and once you do that, your function is set, and it's a 1D function in theta.
So you're not wrong, and maybe I'm just confusing things. So maybe Faust can help explain this. I'm just saying you don't have to fix d. It's not a required. This equation is mathematically correct even if you don't fix d.
Mm-hmm. Yeah.
I kind of have a kind of middle ground, kind of my takes on this. And so usually we will see function as something that if there is variable in there, we would plug in and get some value of it, right? In a mathematical sense. But for the function on the left, I'm not sure I say this correctly or not, likelihood. The given part is usually the variable that we plug in, and the D part here is usually the possible, define the possible outcome. So if you look at the second part of the these functions where we get theta and then the 1 minus theta, that's the one that we plug in the value, right? And the yn there is the possible outcome that's defined in D. So in a sense, we need two variables to kind of complete this function to get some value. But the theta is the value that we plug in, and D define what's the things that we can get when we define the sample space. Does this make sense, Roger?
Yeah, I think so. I'm not sure I differentiate that from what Ted was saying, but we definitely need both D and theta to understand the probability density at that point.
Yes. So what I'm trying to say is that we plug in theta, but for D, we not plug in D. D is defined as a possible outcome. So what is affect the variable y in there. Yeah.
So I'll be brief and then let Dave go and see if he can help clarify. I'm saying that as far as I'm concerned, on the left, it's a function of two variables. And in terms of usage, technique-wise, you might plug in one, you might plug in the other, but that doesn't change the fact that it's a function in two variables.
Yeah.
So
thanks, Ted. So in terms of looking at it, you are right that this is a variable of both D and theta, but the way the difference comes is in how you interpret the statistics. So in the Bayesian statistics, as we'll read when we go to the definition of frequent test statistics 3.3, they will talk about what's the key difference. And in Bayesian approach, they view probability in terms of information rather than the repeated trials. And which is what I think Jayant is trying to say, that, well, D is fixed in this case. There's one trial or one set of data, and based on that, you're trying to work through to get to the inference subsequently. Versus if Yes, the equation D is a variable, but if you had the opportunity to collect multiple data, then the frequentist approach comes in, where you are looking at multiple trials to then adjust your theta as you go along. So that's where the difference comes in. But if you look at the equation as is, yes, it is an equation of two variables, but how to interpret in different contexts is what makes the difference.
Okay, that's good. So probably in all of chapter 3, except for section 3.3, when you see P of D given theta, we're talking about for just one set of data D. That's a fair
Right.
point.
And one other thing, if I may add, is that theta is the unknown here. We are trying to figure out theta. And so even though it says P of D given theta, we really, you know, the given theta kind of might mean that you know
Backwards.
theta, but you don't actually.
Yeah.
Sure.
Well, actually, in this case, wouldn't it be, Janeth, in this case, that theta is the prior theta?
The theta is what you're trying to figure out. You're trying to figure out what the bias of that coin is. What is the
Right. So that's
probability?
so you're trying to figure out the posterior, but isn't your prior? You've already made an assumption, right?
The prior, yeah, you can make an assumption of half, for example. You can say the best guess I have.
Right.
Of a
Or
coin
whatever. Yeah,
is
you might,
half.
if you believe it was
But-
fair. Yeah.
But what you're really trying to figure out is P of theta given D, which is, you know, which is your
That's
best estimate.
this.
Yeah,
That's
which
what
is
we're trying to figure out. But we're
Correct.
using this, which I thought was what's the likelihood of this data under your prior assumption of the theta.
correct. Under what you have observed. So you don't know theta, right? You just keep it as a variable. You observe D, and then you and then you have that equation which is below this page, you know, below the fold here. Yeah. So you get equation 3.2 based on the observed data D. And that is the form of your function of theta, which is what you're trying to determine.
So this equation is, they're calling it the likelihood. And the likelihood represents our beliefs about what data we expect to see for each setting of the parameters. And they didn't say it, but theta.
Right. So if your coin is unbiased, then you can put a value of half, and that's what you would
Yeah,
get. Right?
yeah.
And so, but you don't
If you
know
believe
theta.
if your prior is that it's unbiased, yeah.
Yeah, you don't know
Yeah.
theta. At this point, you're
Yeah.
kind of, the prior is only to kind of make that, you know, plug it into that equation.
The prior
But
goes up
over here, theta is a variable which is what you're trying to figure out.
the posterior, yeah.
So at the risk
Uh,
of spending even longer on this, okay, just so you get the right understanding, the prior is not a fixed value. It's also a distribution.
Yes.
Okay, so you're saying in your prior, how likely is it that, for example, 0.5, the coin is fair? How likely is it that it's 0.6? How likely? It could be a uniform distribution. It could be a distribution that has a peak at certain values, whatever. It could be multimodal, bimodal, whatever, okay? So the likelihood, I like the way I think it was that Jayanth said it, you really should think of theta as the unknown.
Okay.
Okay, so don't even worry about the prior. Just think of it as an unknown.
Okay. Yeah, they say that later on, right? Where it's the in Bayesian, the parameters are the unknown and the data is treated as fixed, period.
Right.
Yeah, it's like, imagine somebody gave you a coin and you don't know what the bias of that coin is. How do you figure out the bias of that coin? You would toss it a bunch of times, n times. And you note down how many heads you got and how many tails you got. And then you plug it into these equations to figure out what theta is, which is what the bias of that coin is.
Okay, I'm going to move on, given that it's 7 p.m. and we're on the second page. Okay, so this sufficient statistics was a new term for me. As I read through it, it's all the information that we need to know about the data in order to infer the parameters. So in this case, the order, for instance, wouldn't matter. So that's not part of sufficient statistics. Just the two counts are sufficient in this particular case. So this they are calling this, I think he called the Bernoulli likelihood. And what we're saying is that there's another function called the binomial likelihood model, here defined here, which captures, it has some extra junk in it, but it captures the same form of parameter theta to the y power and n minus y. So this y is now a count of ones versus zeros, event A versus event B. And they're basically saying we can use that, given that we only need the counts up here for sufficient statistics for this, we can substitute in this distribution for the likelihood. And it works out, they say, let's see, we say it's proportional. So this term goes away, it's proportional to the Bernoulli likelihood equation in 3.2. Okay, and it turns out that format is nice later on. Is this where they talk about? No, okay, later on they talk about being able, okay, down here it is. All right, so that's enough for the likelihood that we talked about. The prior then is our belief about the distribution of the parameters before we get started. And what they're saying is we could start with a uninformative prior, meaning it has kind of minimal information, maximum entropy, I guess. We could use uniform if we want to say that we don't know anything about whether it's biased or not. But rather than do that, we're going to put it in this form. We're going to use the beta distribution. And the beta distribution can behave the same way as a uniform distribution if we assign this alpha and beta up thing to 1. So that was one that one of the complaints I had about the first part of the chapter is it didn't really talk about the distribution. They introduced in the distribution, but didn't really talk about why you would use one, how it's useful, et cetera. So this beta distribution, I went and kind of looked up, and here's the different forms based on the different parameters that you put in. And it represents this probability distribution for a binary event, is the way I understand it. And I had here, I found a live calculator of it. So if we have both alpha and beta set to 1, then you recover, this is a PDF of 1. And if you start to increase this, so this is, if I roll, so it starts with 1 for both. It's, I think it's beta plus 1. If I roll one head, then it starts to roll towards one end of the spectrum. If I add the other, now it's balanced. So it's thinking the most probable, the highest density is in around the middle. And as we add the number of counts to this, as we increase, now it's defined continuous, but in this case, we're using it kind of as, a count. So if, and this would be 1 plus 2 is 3, 1 plus 2 is 3. So after 4 rolls, if we get 2 heads and 2 tails, we get a distribution like this that's saying, well, the highest probability density is in the middle, not on the ends. And if we roll a bunch of them and they're balanced, you can see that the variance starts to squeeze in and it gets more and more confident in that center value. Likewise, if there's a bias in them, if you're getting more of one rather than the other, you can see that the distribution, would it be the mode, I guess, or maybe it's the mean, shifts to one side or the other. And I think that also, if you have a small count, you can see it, especially this would be no A's and 2 B's, gives you a shift like that. So anyhow, that was that distribution I hadn't seen before, and it kind of, looking at it now, I can see how it works really good for these binomial types of models. Any questions, comments?
If I may add some intuition.
Mhm.
If you get equal number of heads and tails, you get this nice symmetric distribution. So the x-axis here is the probability of heads, the theta that we're trying to
Right.
determine. So if you get equal number of heads and tails, then your coin is probably fair, and therefore your best likelihood is at 0.5.
Mhm.
And if you get equal number of heads and tails over a large number of experiments, then you have more and more confidence that it is fair, and therefore your distribution narrows. Does that make sense?
Yes. Yeah.
And the other way to look at it is, if you get more tails than heads, then is the other way. So the alpha will be less than beta. So then the probability of heads is small, right? If you get more tails.
Mhm.
And if you reverse it, then it skews the other way, and you have more confidence in the coin being biased towards heads. And same argument here about the number of trials. As you increase the number of trials, the distribution narrows, and you become more and more confident that
Right.
Whatever the value, let's say you have a maximum likelihood, you take the maximum value, you become more and more confident that is the value of the bias of the coin.
Yep.
Yeah, so that's an excellent description. So think of beta
Hey,
distribution.
Dave. I'm sorry. I'm going to recommend that we move on. Okay. Like, I like the intuitions, but and I'm not picking on you personally. I'm just trying to maybe push us a little bit to get through more, just because there's so much material.
Okay, so that was my introduction to the beta distribution. And in here, they're showing kind of the effect of these counts and the strength of the prior. So in this case, a prior of beta 1,1 basically is that uniform distribution. It means I have no coin tosses to base on. And when you add in whatever the sequence was, n1 equals 4, n0 equals 1, it shifts it. And the posterior gets shifted completely towards whatever the likelihood yielded. If you have a stronger prior, in this example 2, then adding this new data likelihood, you get a shift, but it's in the direction, it's gone from your prior to the likelihood, but not all the way. It was kind of tugged in that direction, but didn't go all the way.
Yeah.
Okay. Let's see. I guess that kind of jumped the gun, because that's probably referenced in this section where we compute the posterior. And here we say that p theta of d is proportional to, so this would be the likelihood, and this would be, excuse me, this must, yeah, that's the likelihood, right? And this is the prior. Likelihood times the prior. And when you can see just by factoring out the thetas and the 1 minus thetas that you get the equivalent of a beta with the alpha hat plus n1 and a beta hat plus n0. So it shows that multiplication, and they did use the proportional here, so they ignored that the denominator that we had talked about before. Because the form of the posterior is the same, in the same family as the prior, they call this a conjugate prior. And it's the conjugate prior, it's conjugate to the binomial distribution. But that's kind of the definition of it. I don't know if we need anything more on that. I did look at conjugate priors in Wikipedia, and they have a whole table of, if you use this likelihood, then this is the conjugate prior. Here's the formula for the posterior, as well as here's the closed form formula for the predictive probability. So I'm going to move past that since we're running short on time, but I would assume that's how I do it in the future. As I go there and I say, this is what I got, I go look up the formulas in there. But for this one, we're going to also do something where, so this computed the complete posterior distribution for theta. There is a point estimate that you can do where you say the argmax of that theta given d is equal to, so the first thing they do is just take the log of it, because the argmax of theta of the function is going to be at the same point as the argmax of the log. And because we're dealing with multiplication of lots of small numbers, computationally, it's a lot easier to deal with logs and summing up the logs rather than trying to carry out these long multiplications with precision or with floating point. But they say that then that is equal to this equation over here, which I believe is just this Bayes rule, theta times p of d minus given theta divided by d is how I get the log of a multiplication is a sum. So the probability of theta plus the log of the probability of d given theta. And they didn't include this term. I wrote that in. My assumption is that's because d is not a function of theta, so it doesn't affect the argmax. Any comment or questions on that?
That's correct.
Okay.
It does not affect it.
Okay. And then using calculus, blah, blah, we show that. I did not derive that equation, but I have a link and I can post it here. A good mail list, not mail list, a good video set. How do I shut this thing up? There's a link I had to this this playlist. I forget what the essential probability. That's a full walkthrough of that derivation if you're interested. It's a whole series on Bayesian statistics, so a good source. All right, so given that they say that if you start with a uniform prior, that the estimate, this point estimate is the n1 over the n1 plus n0, heads over the total tosses. If you start with a stronger prior, beta 2,2, then you end up with this one. That is, they call it add one smoothing. So one observation, I guess it is completely clear, is that, so in this case, we just derived the full form posterior. This MAP, maximum A posterior or something like that, is the highest value, the maximum, at the point of the maximum value of the full posterior. So it's at the mode of that posterior. And it turns out that the mode is of alpha beta, or beta using alpha beta is alpha minus 1 over alpha plus beta minus 2. So you plug those in, you get identical results. So that makes sense. Any questions on that? Okay. They calculate the posterior mean. Here, the expected value of the theta. And it's just this formula expressed as the, let's see, what do they call the lambdas? It's like the accuracy, is it? Or precision? And it represents, yeah. It represents, oh no, it was, sorry, lambda is the ratio of the prior to the posterior equivalent sample size. So anyhow, that's how the formula for calculating posterior mean. Posterior variance, they have an equation for us as well. And it is closed form right there. So those are 2-point estimate values, I guess. Oh, excuse me, those are 2-point statistics on the full distribution. Any comments or questions there? Okay, another point they talk about is moving on then to credible intervals, and they're saying this isn't the same as the confidence interval that we've heard before. So I'm going to just read through. Posterior distribution is a high-dimensional object. It's hard to visualize and work with. A common way to summarize such a distribution is to compute a point estimate, such as the posterior mean or mode, and then compute a credible interval. So what we're saying is that if we provide a single point, we'll provide a region around that point that contains 1 minus alpha of the posterior probability mass. So this is just an interval, and what they're saying is, it can be anywhere. There's a special one, this region called the central interval, where the tails are balanced. So in this picture, they show a PDF, the posterior, and they show a central interval that's centered around, I guess, the mode in this case. Actually, I'm not sure if it's the mode or mean, but anyhow, it's centered such that the area of this little triangle here matches the area of this little triangle here. By the way, how's the video? Am I getting a lot of lag, or is it Ted?
Seems pretty good to me.
Okay. So that's one thing. They do make the point that, this is a little weird, where there's some higher probability events or higher probability density that's included there, and lower on this side. So there's another one, which is called, another way to think of this, another special interval, which is called the highest posterior density, where they essentially balance out that density, pick a density level that's fixed, and that the 5% of these two tails add up to 5% or whatever it is for the what do they call the alpha that you're using. And it makes a little more sense. I had one question I won't dive into here, but this assumes, I guess, if this was a multimodal PDF, I might have little bounces here. So I'm not quite sure how HDP or HPD would work with those, because unless you moved it down below all those valleys, let's say.
Yeah, you would. It's an area under the curve thing. So you just pick 2 lines that have 95% of the area under the curve between them.
Right.
And
it would suffer, though, potentially from the same thing, where you might cut off some higher density areas and keep some lower density areas because it's going up and down. But
I think that if you just nudge it, eventually you can always get them to be the same height.
Okay, so any questions up to that point? Okay.
So we'll get to this when we get to the frequentist stuff, but I read some of the links about frequentist versus Bayesian and stuff, and
Yeah.
I feel like that this is not the confidence interval, but this is what my brain wants the confidence interval to be.
Yes, exactly.
Could be the way I would describe it, but we can go into more detail next
When we
time
get to
when
that,
we
yeah.
actually get to that. Yeah.
And this was I didn't get this initially when I read it, but the idea of this posterior predictive distribution is, okay, now that you've got the model and you want to predict future values, how do you do that? And what they're doing here, I guess, is essentially over all of, so as you pointed out, Ted, theta isn't fixed. Theta is a distribution. And the kind of the prediction for each one of those thetas would be different. So in a Bayesian posterior predictive distribution, you actually will integrate over all of the thetas what's the probability at that point. And so it takes into account, that the ones beyond that central single point estimate. Does that make sense?
Yeah, I don't know that the coin flipping thing lends to it, but you know, if you're trying to find the parameter theta, ultimately it's not because you really want to know what the theta looks like. You know what I mean? It's usually
what you want to
because-
know is what's the coin, the likelihood of the coin, right?
Well, but
And
I'm
so-
saying, yeah, but like, yeah, I'm just saying for coins, maybe it's just too simple of a thing, so it's hard to, for me at least, it's hard. But it's more like once you've figured out the theta for some complex thing, then you can actually make predictions. That's usually why you're doing this in the first place, not because theta itself is the end goal.
Right, right. And I guess the point is that if the distribution over that theta, you know, is using that single point, you might come up with one particular answer, but the way to do it in a Bayesian style is to consider the likelihood of all of these thetas and integrate the results of those likelihoods.
Yeah, so let me say it this way. So I thought of an example. Let's say we're modeling things and we're modeling the way we think students learn, and that my theta, you know, I've got some observed data on test scores, and that my theta ultimately is going to help me describe, you know, the way that students are learning, right? Ultimately, what I want is to predict some kind of like future test scores. It's not because I want theta in and of itself.
Yep. Yeah.
And so then that section you just talked about would be predicting Y is my future test score.
Right. And it's using your full distribution of theta to compute it, not just a single point estimate. And that's, I think, where it kind of differs from the frequentist, which would use a single point. Okay.
You have a hand raised.
Okay, who's got a question?
Yes, that's me, but I'm not sure I'm going to take too much time or not, but just quick question. I'm okay if you do not answer this, but if we don't know all the value of theta, possible theta, can we integrate it over the credible interval, just to get some estimate of a next prediction or something along that line? Is the practice similar to this or not at all?
So somebody else can check me, like Neil, whatever, but I think either for like the coin tossing, we have a clear functional form. So then, you know, we do whatever. Or when we're modeling, we make an assumption. We say, let's assume this is a Gaussian. Well, then now you have a functional form. It doesn't mean it truly is, but you do have a functional form for your assumed Gaussian. And so then if you get like a Gaussian posterior, then yes, you can now find the credible interval. Does that make sense?
Yes, all right, got it.
Okay, marginal likelihood, in this case, it seems like, well, we talked about the evidence one before, but in this case, they're also talking about it where you have a model and multiple models and you're evaluating models. So I won't go into it in detail, but they just include the model as one of the parameters in that distribution. Let's see. Okay, so here was what I was talking about earlier, where they're marginalizing out the unknown parameters, since we effectively computed the weighted average of predictions from an infinite number of models, and that this this act of integrating is the heart of the Bayesian approach to machine learning. So this is where when they can determine the posterior predictive distribution, they use it for all of the thetas in the distribution of theta. In your posterior.
So I think that diagram, figure 3.3, really gets at the heart of it, right? So if you use a point estimate, then you just have a point estimate for your variance. And so you can see that the bars are equal sized everywhere. Whereas the full Bayesian process, you'll see as you get farther away from your training data, it knows that the uncertainty gets larger and larger. And if you got far enough away, then those bars would get absolutely humongous.
Because we have no data out there.
Yeah.
Okay. let's see. Diffusion approaches. Yeah, okay, that's the Emily one that we're talking about. Okay, this was, I think, an important one, is that the uncertainty captured by sigma is, what's that? How do you say that? Aleatoric uncertainty or
it's
intrinsic
aleatoric.
uncertainty? Aleatoric, okay. And this would persist even if we knew the true parameters for the model. But in our case, we also don't know, we've got uncertainty about the parameters. So we have another uncertainty, which is called the epistemic uncertainty. So there's part of it is just uncertainty about the data. I'm taking that to mean like sensor noise, that type of thing. And then there's epistemic, which is more like our model noise. Two things to keep important to keep in context. So the next section, selecting the prior. So one of the, when you read through the history, if you get a chance to read through the history of Bayes, one of the big complaints and why it kind of lost favors for a period of time was because of this selecting the prior. People didn't like the idea that you had to, the author got to choose something, make a guess at something, then that somehow affected the scientific results that came out of it. So it's an important one. Here, they're going to go through a number, let's see, we'll discuss conjugate priors, which is basically, we've covered the one conjugate prior, which was, what was it, for a binomial distribution, a likelihood distribution. The beta is the conjugate prior, yields a beta as a posterior. And there's a whole bunch of them. Like I said somewhere here, conjugate priors, if you look up this on Wikipedia, you'll see a whole table of likelihoods, the conjugate prior form, and they compute the posterior parameters for the distribution, the posterior distribution, as well as the posterior predictive. I'm assuming we don't have to remember everything. We're going to have a table here that we go to look it up later. Okay, so we're going to do that. This one, exchangeability, it made sense to me in the sense that they talk here about background image. So they're kind of challenging this independent. If you have background images in an image, so a dog in front of Mount Shasta and a cat in front of Mount Shasta, there's commonality between those two. But they define this idea of exchangeability, meaning that it doesn't matter what order, they're completely independent. One doesn't depend on the other. That is a more general form of this independence, is what I took away from this. And I think that was Janeth had kind of suggested it's kind of the nth order of, as long as you select randomly, it's independence in the sense that which of the n items do you pick. One thing I didn't get is they say that if you have this exchangeable sequence, we can treat it as an unknown variable theta. So if I have something that meets this condition of an exchangeable sequence, that it's coming from a hidden common cause. And I get that. I get why exchangeability would counts for independent, but I didn't have any intuition why the fact that it's exchangeable. So a sequence of random variables is infinitely exchangeable if and only if for all n we have this definition. The theorem tells us that our data is exchangeable, then there must exist a parameter theta and a likelihood and a prior. I didn't have any intuition why exchangeability implied that there must exist a parameter and a likelihood and a prior. So I don't know if anybody else had anything. Okay, I'll move on.
By the way, I don't think this, I think this is meant to sort of justify and for some people give intuition why Bayesian statistics is good, but I don't think it's required at all to understand and do Bayesian stuff.
That theorem?
Yes.
Yeah,
yes.
Okay, I'll buy that.
But basically they're just saying something along the lines of like, if all the xi's really only depend on theta, then they can't depend on sort of like each other, they just depend on theta. So then the order should never matter because they only depend on theta, but theta's an unknown, but it's not like it's changing on you.
Okay.
Does that make sense?
Yeah, it does. So
One
Ted,
thing,
we're at,
sorry, I was just looking through that again. So one thing here is that it's IID given theta. And that I think is important because they may not be IID themselves.
Right.
They may
If
not
it were
be
IID, then the pi, the multiplication would just be P of X sub I or whatever.
Yeah, so the xi are not independent themselves, but they are independent conditional on theta.
I can't remember, did they say it here? Example they gave was you could have completely IID photos, but if you just had some background picture and you added it to your photo, then they would no longer be IID. They would be this weird correlation between all of them, but they would still be this exchangeable thing. So the theta that they would be dependent on is the one photo that you added, the background that you added to all the pixel values.
Okay.
So if you want like a concrete example.
so is that like the theta is the image that the background image then? Is that what you're saying?
Yeah, or like, let's not even do
it out
background.
and then
Let's
it's
just say
IID.
you add 10 to all the pixel values.
Okay.
They are no
Okay.
longer IID. They've
Gotcha.
strayed from that. But knowing the theta, that was you added 10 to every pixel value, then
Yep.
they're now all IID with respect to that.
That's a
Yep.
good example, Ted. Yeah.
It was either in this book or it was in the reference that was listed somewhere. I don't remember which.
Okay. So that makes more sense. Okay, Ted, it's 7:30. We're just at the frequentist statistics. What do you want to do?
Yeah, so I think this is a natural place to pause. I don't. An hour and a half is already a pretty long time, so I think some people
I agree.
are going to be burned out. So I will repeat my ask to see if there's someone who would be willing to step up. And at this point, maybe we're not finishing, but just to take us through a few more sections of chapter 3 for next week. And again, as you can see, the goal here isn't that you're supposed to be the expert. It's just we're going to, walk through an outline of it. And again, like, Roger had highlighted things. I think if you were here the very first week, I just could have made an outline with the titles of each of the sections and maybe a very brief sentence or half sentence, Anyone?
So the other thing, while people are volunteering, Ted, is I'd ask the question. So we got kind of derailed here for a while and spent quite a bit of time. We certainly didn't get as far in chapter 3 as wanted, but did people find it useful, or would we like to have it more stay on track or to get through, or was the conversation constructive?
I thought it was probably a good idea. The whole book is essentially about Bayesian statistics. So if we need to spend time on the first 2 pages with what is Bayesianism, let's do that. Some of the other stuff, maybe we'll just blitz through, but this is like pretty integral to what the whole book's about.
Yeah, I kind of felt that way. I meant to mention that in the beginning, was that when I was kind of thinking about it, I spent a lot more time on the first 10 pages than the rest of it. I was like, this going through the frequentist statistics, I think, is some important things. And then we start getting into these, all of the this is probably all good. Confidence intervals was a good discussion, and why frequentist stuff doesn't work. Once we got into the conjugate
when we get into
priors,
like the conjugate priors, and there's a list of a bajillion of them.
Yeah, unless somebody knows that some of those are important, let's just zoom through them.
Yeah, they're just going right over my head basically right now.
Yeah. Okay, Ted. So hopefully we'll get some volunteers. I will be in a hotel next Tuesday nights, but I can probably, at least this first part, I've already gone through and kind of have notes. I can help out on that if so.
All right. Well, thank you for agreeing to do another one. Jayanth, maybe can you do whatever part of chapter 3 we don't finish next week in 2 weeks?
Sure.
All right, awesome.
Awesome.
Appreciate it. And then this way we can get through chapter 3. Yeah. And I do think it's going to go faster because like this was good to like pause, like we said, and really you know, see if we have solid. But some of the other stuff, to be honest, it was I don't know. It may turn out to be super important, but at this point it just kind of a lot of it went over my head. And so I'm like, all right, I'll come back and review it if it gets referenced later and it's important.
Right.
Yeah, there seems to be a lot of stuff thrown casually, which to me is like, oh, it takes a while to sink in some of these things that he puts in there.
Yeah. And by the way, I don't know if everyone was here for all the other sessions, but like there is a book 1, which is sort of like the introduction to probabilistic machine learning. And I made the somewhat bold choice to not start with book 1 and just go straight into book 2. But book 2 is a little bit haphazard. It is a little bit like an encyclopedia of everything I didn't fit into book 1. So it's less of like a course and more of just like blah.
Just quick remark that I kind of skimmed through book 1, and it's kind of I would say there's kind of hurdle barrier between jumping from book 1 to book 2, even if you have a solid background on book 1. Yeah.
All right, thanks. All right, everyone, really appreciate everyone who came. Thanks for sticking with us. And then, yeah, so it looks like we'll probably do this chapter 3 for 2 more weeks, and then we'll get into state space models, I believe. Wait, what is it? No, graphical models. Anyway, we'll get to chapter 4 in 3 weeks. And again, graphical models. Thank you. And so we're going through this part 1. I'm not 100% sure what to think of it, but I hope everybody does stick with it. When we get to part 2, when we finish, I think there's like 5 or 6 chapters in the foundations section. Then we're going to talk about inference, and then we're really going to talk about like, hey, how do you compute these things? How do you compute these posteriors? And it's going to get more practical, okay? And then, you know, I have that planned through, hopefully, to get that done by summer. And then if we keep going, you know, summer, then eventually you get to things like, so I think part 4 is generative models. So then we can talk about a lot of the cool stuff that's happening right now with like image diffusion models and other kinds of generative models. So, all right. Thanks, everyone. See you next week.
Thanks, guys. Bye-bye.
All right,
Thanks, Ted.